Hello everybody, welcome back to Physics 331. Today what we're going to do is we're going to start a new topic. What we're going to do today is we're going to review Fourier Series. And what a Fourier Series is used for is to represent a periodic function of time as a sum of cosine terms and sinusoidal terms. The reason we're doing this is so that we can eventually start talking about the more general Fourier transform, which will be used to go between the time dependence of some pulsed signal in time to understand what its frequency content of that signal is. And then, of course, using an inverse Fourier transform, we could go the other way. So if we have some if we know the frequency content of some signal that we're studying, we could do the inverse Fourier transform to look at that signal in the time domain. Okay, and so here I've drawn just a simple periodic function. It's a square wave, and it repeats over and over, and the period of this function is 2 times capital T, and so that's indicated here. So every 2 times capital T in time, this function repeats. What a Fourier series allows us to do is to represent that function of time as a sum of cosine terms and sine terms. The a0 over 2 is some initial offset, and then we have our sum from n equals 1 to infinity over cosine terms with a coefficient an, and sinusoidal terms with a coefficient bn. The angular frequency of our signal is 2 pi divided by the period, but our period is represented by 2 times capital T, and so that means the angular frequency in this case is pi over T. And so we can re-express our Fourier series in terms of omega. And if we do that, our periodic function of time is equal to some a0 over 2 plus the sum from n equals 1 to infinity of an times cos of n, and then we have pi over capital T, so that's omega, and then we have time t, and then the same thing for the sinusoidal terms with coefficient bn. So n omega t. So expressed in this way, what you can see is that the cosine and sine terms are summed over higher and higher frequencies. So as n increases, so does the frequency n times omega. Okay, in order for this to work, we need to have a way to calculate these coefficients an, bn, and a0. And so let me just remind you of how we do that. A0 is given by 1 over t times the integral of minus t to t of f of t dt. And so here for f of t, we would put in the time dependent signal. So if it was a square wave oscillating between -1 and +1, over half the period, f of t would be -1, and over the other half of the period, it would be +1. Okay, and so the time range from minus capital T to plus capital T is 1 period, and so we're integrating this over 1 period. The reason we define the period to be 1 over 2t, the reason we define the period to be 2t is so that this 1 over t out front would just be expressed as 1 over t. So it was just a choice for convenience, but we didn't have to do that. Okay, so that's the one leading coefficient. The an coefficients in front of the cosine terms is equal to 1 over t, the integral from minus t to t, f of t. So all of that's the same, except now we're going to multiply by cos n omega t, and then integrate over t. The bn coefficients have the same form, except instead of multiplying by cos n omega t, we multiply by sine n omega t. And so that's all stuff that I assume that you've seen before. So it could have been in one of your physics courses or one of your math courses. Okay, if you do this analysis for the square wave that we've drawn, let's say that our square wave is going between +1 and -1, then you could confirm, and it's worth just reviewing, that the coefficients that you will find, so for this example of a square wave, you will find A0 equals 0, so the leading term before the sum is 0, and the an coefficients, so that you also find all an equals 0. So there are no cosine terms in our Fourier series of a square wave, but the bn's are not all 0. Some of them are, not all of them. You'll find that b1 is 4 over pi, b3 is 4 over 3 pi, b5 is equal to 4 over 5 pi, and so on. And bn is equal to 0 for all n even. Okay, what we could do is we could make a plot of, maybe I'll do it here, of our bn coefficients. And so this is as a function of n omega, and so here's our bn coefficients. When n equals 1, we get a 4 over pi, and so maybe that occurs here, and so this is 4 over pi. Maybe let's put my bn over here, bn. And this occurs when n equals 1, and then this would be n equals 2 and 3, so this would be 3 omega, and we would get 1/3, a peak at 1/3 that height. And so this would be 4 over 3 pi, and then this would be 4 and 5, and then we'd get a peak that's 1/5 that height. So this is 4 over 5 pi, and so on. You'd get a non-zero peak at 7 omega with a height of 4 over 7 pi, and so on. So the interpretation is that the coefficients an and bn, in this case an are all equal 0, but the bn's have some non-zero values, and what they do is they give the amplitude of each Fourier component. And so all those different Fourier components have different frequencies. There's a component at frequency omega, a component at 3 omega, 5 omega in the case of the square wave. Ultimately, what we're going to do is we're going to end up with doing the same thing for a signal that is not periodic, and we're going to find that instead of getting discrete spikes at different frequencies that are equally spaced, we'll find a continuous spectrum of frequencies with non-zero amplitudes that are required to make up our pulse in time. Okay, so before we get to all of that, what I want to do is I want to re-express this Fourier series not in terms of cosines and sines, but instead in terms of complex exponentials. So that's going to be the first step. So to do that, let's just recall that sine n omega t is equal to e to the I n omega t minus e to the minus I n omega t over 2i. And cos n omega t is equal to e to the I n omega t plus e to the minus I n omega t over 2. So all we're going to do is we're going to go to our original Fourier series in terms of sines and cosines, and we're going to replace the cosine with the e to the I n omega t plus e to the minus I n omega t over 2, and the sine with the e to the I n omega t minus e to the minus I n omega t over 2i. So it's not surprising that we can also formulate a Fourier series in terms of complex exponentials. Okay. So, in fact, let's do it a bit of a different way than I said. Let's just start by assuming that we can take a Fourier, a periodic function, and express that function of time as, again, just some coefficient, some constant offset c0, and we'll have a c1 e to the I omega t, and then we'll have a c minus 1 e to the minus I omega t, and we'll have a c2 e to the 2I omega t plus c minus 2 e to the minus 2I omega t, and we would have, say, the terms with 3I omega t and the terms with 4I omega t and so on. Okay, so that in general, this could be expressed as the sum from n equals minus infinity to plus infinity of cn e to the in omega t. This works for n equals 0 as well, because then you just get a c0 e to the 0, which is just c0. So we still get our constant c0 coefficient as well. Okay. So one thing that will be useful going forward is just to make note of one particular result. So let's make note of a useful result before moving on. And it's pretty easy. So what we're going to do is we're going to divide by 1 over 2t. So 2t is a full period, and then we'll integrate from minus t to t. So we integrate over a period, and this is e to the I k omega t, and we'll integrate over time. Okay, and so what we're going to do is we'll specify that k is a non-zero integer. So it's maybe plus 1 or minus 1 or plus 2 or minus 2 or so on. Okay, you know, of course, it's just an exponential, so this integration is very straightforward. When we evaluate the integral, we'll get a 1 over I k omega, so that overall we have 1 over, let's see, 2 I k omega times t. Okay, and then we'll have, evaluating at the upper limit, we have positive t, so we have e to the I k omega capital T minus e to the minus I k omega capital T, evaluating at the lower limit of integration. Okay, but this is just 2I sine k omega t, and omega t, if you remember, let's see, t was half a period, so 2 pi over 2 2t was equal to omega. So then pi over t is omega, so then omega t is equal to pi. Omega t is just equal to pi. And so if we substitute those things in, let's see what's going to happen. The 2 i's will cancel. The omega t just becomes a pi. And so what we have then is this is equal to 1 over k times pi sine of k pi. But k is an integer, and sine of some integer multiple of pi is just 0. And so this is 0 for all cases. All right. Good, except k equals 0, okay? Because then we have a 1 over 0 out front. So that one we have to just be a little bit careful of. All right, so let's then think of evaluating. So let's now evaluate the integral from minus t to t of 1 over 2t of, 1 over 2t of f of t dt. So what's that going to equal to? So we'll go back to our series, our assumed series of complex exponentials. The first term is just c0. So the first term will just be c0, 1 over 2t minus t to t of dt. But then this is all just a 1. And then our next term is going to be a c1, and then we're going to integrate e to the I omega t. Okay, so then we have plus c1. Sorry, I wrote pi again. This is 1 over 2t. c1, 1 over 2t, the integral of minus t to t of, so that second term had an e to the I omega t dt. Okay, but by the argument that we just made up here, the integral of e to the I k omega t, where k is a non-zero integer, always vanishes. And so this is just the k equals 1 case that we considered above, and so this is going to be 0. And then we have a plus c minus 1, 1 over 2t. I can't stop writing 2 pi. These are 2 t's. Integral of minus t to t, e to the minus I omega t dt. And this is just the k equals minus 1 case. So it's a non-zero integer, that goes to 0, and we would keep going and find the k equals 2 case, that would be 0, the k equals minus 2 case, that would be 0, and all of the terms would be equal to 0, so that finally what we would end up with is just c0 is equal to 1 over 2t, the integral from minus t to t of f of t dt. And so for our assumed series, we've now found the value of the c0 term. We just now have to find the values of all of the other coefficients, the c1 coefficient, the c minus 1 coefficient, c2, c minus 2, and so on. Okay. So next, we're going to consider the following integral. It's the same 1 over 2t integral from minus t to plus t of f of t. So far that's all the same. But now I'm going to insert an e to the minus I and omega t, and we'll do that integral. Okay, so first of all, our series in terms of complex exponentials starts with a C0 term. So it would just be C0, 1 over 2t, integral of minus t to t, e to the minus I n omega t dt. But this is just the k equals minus n case. K equals minus n case. N's an integer, and so this is going to vanish. And then we'd have plus c1, 1 over 2t, integral from minus t to t, e to the, let's see, the c1 case is going to be e to the I omega t, and then we're going to multiply by e to the minus I n omega t, integral with respect to t. So this is just the case where k equals minus n plus 1. So this is the k equals minus n plus 1 case. That's just some integer, and this will evaluate to 0. We'll do a couple more. So there's the c minus 1 term, 1 over 2t, integral from minus t to t, e to the minus I omega t, and then multiply by e to the minus I n omega t, integral with respect to t. We can combine the two exponentials, and we would have the case where k is equal to minus n minus 1, which is an integer, and this integral will vanish. And this will keep happening. We'll keep having all of our terms vanish until we encounter the Cn term. In that case, we're going to have 1 over 2t, integral from minus t to plus t. And so the Cn term is going to have an e to the I n omega t. And so we'll have the e to the I n omega t, and then we're going to multiply that by e to the minus I n omega t. So there's a negative sign in there, so this is going to be e to the minus I n omega t. And then we're going to integrate with respect to time. Okay, of course these two exponentials just cancel each other out, and then we integrate 1 times dt, which evaluates to 2t, which cancels with the 1 over 2t out front, and so this is going to evaluate to 1. And then there's more terms, like there's the c minus n term, the cn plus 1 term, and those will all evaluate to 0, and the only non-zero term is the cn, and so we would have that cn is equal to 1 over 2t e to the minus t to plus t f of t e to the minus I n omega t dt. And in fact, this covers all cases. This is n equals minus infinity to plus infinity. It includes n equals 0 because when we put n equals 0, the exponential vanishes. So c0 is just 1 over 2t, integral of minus t to plus t of f of t dt. All right, so I think that's where I'm going to stop for right now. In the next video, we'll do one example of a Fourier series using the complex exponential form, and then we will start thinking about the Fourier transforms of non-periodic functions of time. Okay, thank you very much.